So chapter 5 is about generation and migration of petroleum. So contents, it has we'll talk about the original petroleum and modern organic process on the Earth's surface. These two talks about how the petroleum is being generated. And the formation of the kerogen is also about the origin of the petroleum. And so section 5.4 and 5.5 is about the migration to the reservoir. So you have a source rock where the petroleum is generated, and then these disseminated hydrocarbons should migrate somewhere and then gets accumulated to be commercially productive. So we're going to talk about that in the last section, two last sections. Okay. Good. So this chapter discusses the genesis, migration, and maturation of petroleum. The precise details of petroleum generation and migration are still debatable. So there's no particular answer. So still, the geologist is particularly interested in these topics. So their question is how this becomes the petroleum. What material has been transferred to the petroleum, and what was the condition for it? And the theory of petroleum genesis must explain the two sets of observations. So from the experience from many years of petroleum production and exploration, they found that the major accumulation of the hydrocarbons occur in the sedimentary rocks. So you don't find much hydrocarbons in metamorphic, right? Or the basalt, right? Basic. So most of the commercial hydrocarbon accumulation was found in sedimentary rock, like the sandstone or the carbonate, the shale. And numerous examples of hydrocarbon accumulation are totally enclosed above, below, and laterally by the impermeable rock. So it's like that you have a closed system, and you have to have a closed system to have the major accumulation. Otherwise, it can migrate and it will disappear. And traces of the indigenous hydrocarbon have been found in igneous and metamorphic rocks. However, the commercial accumulation in basement are always in the lateral fluid continuity with the sedimentary rock. So what it says is that you may find some minor, very small amount of the hydrocarbon in metamorphic and the igneous rock. But in that case, you have that geologic structure is always associated with the sedimentary basin. So you may have some sedimentary basin laterally connected to it, or maybe you have a sedimentary rock above it or beneath it in this igneous or metamorphic rock. So this is very important finding, and geologists were very curious why this is commonly found in the hydrocarbon reservoir. And there are also the chemical facts and crude oil. So this deep oil you find in the hydrocarbon reservoir have differences from the recent hydrocarbon and the affinities with the recent shallow hydrocarbon. So difference is that this crude oil has preference for the even number of carbon chains. That's very odd. And it contains more than 50% light hydrocarbons. And the similarity between this crude old oil and this young shallow hydrocarbon is that they both show the level rotation, which is the optical activity characteristic of the hydrocarbon produced by the biosynthetically, and contains certain complex molecules that occur either in molten and organic matter or as a product of their degradation. And also, they found the correlation between the source rock and the reservoir oil from this gas chromatography. We'll talk about it in the section 3, which is about the kerogen. So the basic question, the two questions that we want to explore this chapter is that this and this. So whether this hydrocarbon is from organic origin or inorganic origin. So in other words, it could be from the biological origin, or it could be from magmatic or the cosmic origin, from the deep earth. And most geologists believe it is from organic origin, so it's biologically generated. And how petroleum is formed from its parent material, so must have only the vaguest idea as to how it forms. Still, there are no true answer for it. So let's talk about the origin of petroleum first. So there is now clear evidence for the origin of abiogenic hydrocarbons in deep crust or mantle, and its emergence along faults and fractures, notably in mid-ocean ridges and intracontinental lifts. So from carbon isotope analysis, if we analyze the C13 and C12 ratio, we can identify whether it's from the microbial activity or it's from the thermogenic carbon, right? So the bacteria prefers to eat up the light carbon. So if the carbon is from biogenic, then the C13 will be less than the thermogenic carbon. Right? So from that analysis, we can identify whether it's from thermogenic or biogenic. And people found that in mid-ocean ridges and intercontinental lifts, they found that there are some abiogenic hydrocarbons. So on Earth, you have a hydrocarbon from biogenic and thermogenic. And how this thermogenic is from? Where is it from? Why you have a hydrocarbon deep inside the Earth? That was the question that geologists want to answer. So they proposed 3 theories for inorganic origin of hydrocarbon. First is the abiogenic cosmic origin, and the second is the hydrocarbon is from mantle. So abiogenic mantle theory. So, and it's also called as Gold's earthquake outgassing theory, which is suggested by this Gold. And third theory is the Fischer-Tropsch synthesis, which is intermediate theory between abiogenic mantle theory and the shallow biogenic theory. So let's briefly look at each theory. Cosmic origin theory is actually it's common from the scientists because they found the methane in the other extraterrestrial area, like Jupiter, Saturn, right? Mars, you found methane, right? And then this methane should be from, like, they produced when there's a universe is created, right? So, and this extraterrestrial hydrocarbon should be also inside the Earth. That is the theory. So this theory is called the cosmic origin theory. So Earth's interior contains vastly more oil than the man have been able to recover, and the belief has been widely held by many scientists, chemistry, and astronomers, but not by geologists. So because if this theory is true, hydrocarbon will be commonly associated with igneous rock and the areas of the deep crustal disturbance and faulting, but it's not. So if the cosmic origin theory is true, like, this hydrocarbon should be anywhere inside the Earth, so that if there's any fault connecting to the mantle, then we should be able to find this hydrocarbon seeping through that fault. But the truth is they don't found it, and we haven't found it yet. So this theory is not very strong in that sense. The second theory is the hydrocarbon is produced and seeped from the mantle. It's called the mantle origin theory. And in this theory, the faults play a very important role. So faults provides the conduit kind of a flow path for the hydrocarbon to migrate to the subsurface. And so if the faults are impermeable, then they can close the system and it will seal to the petroleum migration. And if the faults are permeable, then you will allow the upward movement of the oil and gas, and sulfur is a conduit for the flammable gas, so that the Gould in 1979 suggested the abiogenic hydrocarbon migrates to the subsurface through the fault, and that happens when there is an earthquake. So the theory is that when the earthquake happens, that it compacts the sediment and it compresses the fluid, so fluid escapes through the fault. And so in that instances, the outgassing happens, and that allows the methane to escape from the mantle. And it's been found that there are some spots with the abiogenic hydrocarbon from like hot spot, like the mud volcano or the thermogenic, very actively thermogenic hydrocarbon is seeping out. So that the outgassing theory is, in some sense, it makes sense. It's one of the theory explaining the abiogenic hydrocarbon. And the last one is that the intermediate between the abiogenic mantle theory and the shallow biogenic theory. So this Fischer and Tropsch reaction is well-known industrial process that is used to produce a synthetic hydrocarbon. And CO2, carbon dioxide, and the H, hydrogen are passed over a catalyst hematite and the magnetite at temperature in excess of 500 degrees C. Then you have methane and ethane and propane, this kind of a hydrocarbon gas is generated. So you have to have a CO2, the carbon dioxide, and the H. And the rock mineral can be a catalyst, and also with the high temperature, then you may have the production of the hydrocarbon. So this Fischer-Tropsch synthesis can happen in nature, where in light of the plate tectonics. So if you think about the very hot region, it could be the boundary between the tectonic, the plate boundary, because the tectonic activity is very active there. So the hydrocarbon could be generated in the convergent plate boundaries, where the sedimentary rock and the oceanic crust undergo subduction. Carbon dioxide could be formed from the metamorphism of carbonate. So to be convincing, so to make this theory strong, you have to have you have to explain the origin of the carbon dioxide, right? So where this carbon dioxide can be produced. This carbon dioxide should be supplied to produce the hydrocarbon. And this carbon dioxide, they explain it can be from some carbonate. And hydrogen and the iron oxide could be formed from the serpentinization of some mineral, where the iron oxide is used to catalyze the reaction. And there are some critiques also about that. So in summary, the indigenous oil in basement are rare and not commercially important. Not only are the volume of the hydrocarbon trapped in this way insignificant, but also the reservoir are impermeable and not fractured. So even though you found this indigenous oil in basement, like the igneous rock or the metamorphic rock in the deep region, it's not commercially feasible to produce it. So people don't research this question very actively. Commercial accumulation of the hydrocarbon in igneous rock only occurs where the igneous rock intrudes or are unconformably overlain by sediment. So sometimes you have magma intrusion like this from the deep mantle, and they get cold and it becomes the magma intrusion. And in that area, you may have the hydrocarbon like this structure. So in the black region is the oil. And the rest of the formation is the sedimentary rock. So this is the special case you found the commercial accumulation, like the large reservoir of the hydrocarbon in the igneous rock. Okay. I think this is the repetition. This is just a summary. And so geologists conclude that the commercial quantities of the petroleum are formed by the thermal maturation of the organic matter. So not from the inorganic carbon. So organic is the origin of the hydrocarbon. And this is now examined. So then let's talk about the organic carbon. So we saw that inorganic process that can produce the hydrocarbon. And now that we'll talk about the organic process that can produce the hydrocarbon. So these are just basic facts. The total amount of the carbon in the Earth's crust has been estimated to this number, 2.65 times 10 to the 20 gram. And 82% of carbon is locked up as carbonate in limestone and dolomite. And 18%, the rest of it, occurs as organic carbon in coal, oil, and gas. So this includes the coal and the petroleum together. And conversion of the inorganic into hydrocarbon is photosynthesis. So the main reaction to produce the hydrocarbon is the photosynthesis. You have a carbon dioxide and the sunlight, then they will produce the maybe glucose or cellulose, lignin, protein by the bioactivity. And the glucose is the starting point for the organic manufacture of the polysaccharides and the other complex carbon compounds. So because this is the just basic unit for the polysaccharide. Right? The polysaccharide is the chain of the glucose. The plant, animal die, and their organic matter is oxidized to the carbon dioxide and water. So you have this might be better to explain it. So you have a cycle of the organic carbon. Let's start from here. You have a carbon dioxide and the water. And from the photosynthesis, you have some like plant growth and the animal growth, and they die, and you have bacterial decay, right? And this buried organic matter can be preserved in the subsurface, in the sedimentary rock. Right? So this organic carbon can be preserved, and this will transform to the coal, oil, and gas. Right? And they uplift and weathering. And when they expose to the subsurface and to some certain environment, they can be oxidized to the carbon dioxide. And then so you have a cycle of the organic carbon like this. Again, this will be oxidized to the carbon dioxide again. And then photosynthesis. So I think you remember that from high school, middle school, chemistry, the hydrocarbon is like petroleum is produced from the animal body, and the coal is produced from the plant body, right? But actually, there's no borderline. So you have a very gray area. Petroleum can be also produced from the plant. So that people just think that this whole thing is organic carbon. Okay, so living organic matter, so if you die or if the plant dies or the animal die, or it can be just plankton, right? Very small creatures, they can die, and then it becomes the four major components. You can crack down to the four major components. One is the protein and carbohydrate, lipid, and the lignin. I think you've heard of it. Protein, largely found in animal, and carbohydrate, it includes the sugar and the glucose and some polysaccharide. And lipid is insoluble in water, so similar to fat. Right? And the lignin is like the tree stem, a very hard and stable material. It's like the cellulose. And polyphenol of the high molecular weight. So then, this is the ratio of the organic matter of organisms. So this is the oak leaves and the plankton, phytoplankton, and zooplankton, and spore. So you can see that in the leaves, lignin is quite a major component, and carbohydrate. And zooplankton, you have a nitrogen compound, and carbohydrate, and the lipid. And when they are found in the sea, oceanic condition, in the subsurface, this is the shallow recent sediment, you have a lignin component remain, and nitrous compound remain, and the carbohydrate lipid. You don't find the protein that much. The protein is very rare. And this type of the organic matter will be transformed to hydrocarbon. Maybe but this may be lignin is the mostly converted to the coal. Maybe the other component can be to the maybe aromatic oil or the asphaltene or the paraffinic oil. Good. So then, see, the amount of the organic matter buried in sediment is related to the ratio of the organic productivity and destruction. So if you think about the oceanic, the marine environment, like the coral reef or the continental margin, right? You have organic matter coming from the stream, from the inland, and they will die and they can bury. And so the rate of the burial is the function of the sedimentation rate, and organic productivity also related to it. So you have to have the deposition of the organic rich sediment is favored by high rate of the production of the organic matter. So the organic productivity or biological activity should be very active. And the high preservation potential. The high preservation potential is that if the sedimentation is very slow, then the organic matter can be decomposed by the other reaction, right? By the oxidation or redox reaction, or the microbial also, the bacteria can decay it. So then you have only the CO2 remaining after that. So you have to, there should be some preservation mechanism to keep the organic matter before it converts to the hydrocarbon. And then, so this. So the carbon will be deposited, right, in the lake. So this is the lake. And you have a sediment coming, keep coming. Right? And this sedimentation rate should be high enough to preserve the organic matter. And at some point, this will go, the depth of this area should becomes deeper, and the temperature is proper to produce, transform to the hydrocarbon. Right? That was above the 60 degrees Celsius. Right? So we talked about it in the previous chapter. I think the 60 degree to 120 degrees Celsius. That kind of range is the temperature range should satisfy to transform and to produce the hydrocarbon from the organic matter. Okay, so the all organic matter is originally formed by the photosynthesis, as we talked, and pelagic phytoplankton and benthic algae is the major organic matter. And the physical fact is that you need to have the temperature and light, and amount of light is dependent on the depth, latitude, and turbidity of the water. So this is about the organic productivity, right? How fast and how much organic matter is being produced and that they can be deposited. The amount of the organic productivity is highest in the shallow photic zone, so where the light is coming, and decreases rapidly with increasing water depth and decreasing light and temperature. So the gray area here is the region where the biological activity, biological productivity is very high. So the low productivity is in the polar region and center of the large ocean because it's too warm. And the high productivity is two belts along the east side of the ocean, west coast of North America, here, and the Africa. And the region of the high productivity is the high latitude of whaling. So you need to have deep circulation of the ocean so that the water can mix up well, because that mostly the photosynthesis will be active in this region, in the shallow water region. And if there's a water circulation, active water circulation, then this organic matter can produce more and more, can be produced more and more, so that you have a high activity, high productivity. The area of the high oceanic productivity are not necessarily the area where the organic matter is best preserved. Preservation, so to preserve the organic matter requires two facts: anaerobic bottom condition and the rapid sedimentation rate. So preservation of the organic matter means that it's opposite to the high productivity. So water should stay there. If you have well mixing up of the water, then this organic matter can be decomposed by the sun and it can be diluted. Right? So anaerobic bottom condition means that it's a stationary or restricted water movement. So the water is not moving in that area. It means that there's no oxygen. So you don't have oxygen so that they don't decay. And the rapid sedimentation rate means that there will be the sediment coming up, and so that you can go deeper and deeper faster. Huh? So this is the good graph showing that the preservation versus the sedimentation rate. So it shows that as the sedimentation rate increases, that the total organic carbon in the sediment also increases to a certain point. when the sedimentation rate is slow, the organic matter can be oxidized on the seabed. And rapid deposition dilute the organic content of the sediment. So the optimum rate is somewhere here for the preservation of the organic matter. If you look at the sedimentation rate here, what is the unit? Unit is the meter per million years. So like 1 meter per million years. So it's a very long geologic time. Another important condition favoring the preservation of organic matter is the presence of stratification. So rapid sedimentation rate is also important, and you need to have the stratification of the water. So this means that restricted movement of the water. So you have no circulation, deep circulation of the water. There are 4 major settings for the formation of the organic-rich sediment in anoxic environment. A to B, we will have the 4 conditions. And let's look at briefly one by one. First one is the freshwater lake. And thermally induced stratification of water. So you have a density difference between the shallow water and the deep water. And denser water, you have a denser water deep down, so that this denser water doesn't move. They stay there in the deeper depths. And life will thrive in the upper zone. And in deeper layer, oxygen will not replenish it, so they don't. There's no supply for the oxygen because it's dark, and detritus deposited in the lake bed, so that this dead body will just bury and will settle down in here. So this is the case that you have a high preservation. And second is that the barge basin. You have some like dunes like this structure, and it blocks the water circulation. And the stratification due to the salinity contrast. So density here. So first you have a seawater coming in, and then in this water evaporates, and the salinity increases, and when the salinity increases, the density will increase too, so that you have a high salinity region, and the water is more denser than the shallower one, so that this water doesn't move. Then you have a high preservation. The other is that you have in the continental shelves, you have some region of the stratified water. So in this gray area is the anoxic condition. And if you look at this graph, here from 200 meter to 1.5 kilometer, in this region, you don't have oxygen that much, right? This is called the anoxic region. And in this case, water is stratified, and the organic carbon can be preserved also. And in an anoxic ocean basin, so it's a very deep ocean, and it's okay. So it's been okay. No, there's no now recent instance. Most modern oceans are reasonably well oxygenated because of the deep ocean circulation. But in the past, deep ocean circulation may not have existed in the past period when Earth has a uniform equable climate without the polar ice cap of today. So in the in old days, if you go back, there's no water circulation, so that ocean, deep ocean was deep ocean basin was the anoxic condition. At such time, global anoxic events may have been responsible for the worldwide deposition of the organic sediment. This mechanism explains the extensive Upper Jurassic, Lower Cretaceous black shale that occurs in so many parts of the world, notably in the Atlantic Ocean. So geologists think that there was some time period, there was no water circulation, oceanic circulation. And that was at the time of the late Mesozoic area. And so the organic matter was buried all around the world at the time. And then it's been preserved so that they converted to the hydrocarbon. And so the 80%, 85% of the world oil was sourced from the late Jurassic to the early Cretaceous formation. So the reason that we found many source rock from this era is that there was time that the deep ocean was anoxic condition. So Cretaceous era, no, it's not very important. Let's skip with that. So we've seen the organic productivity and the preservation in the oceanic environment. And this is the case when you have the continental environment, so in the onshore. Onshore oxygen content is constant, the water and number of growing days per year. So in here, because it's on land, we are talking about the tree and the crops. And vegetation. So the rate of the production versus decay increases from 0 degrees C to the 25 degrees C and begin to decline. Preservation potential of the organic detritus decline above 25 degrees Celsius. Okay. Whereas the oceans appear to contain diverse plant and animal life since way back in Precambrian, plants only began to colonize the land towards the end of the Silurian period, and the extensive coal formation did not begin until the Carboniferous period. So chemical composition of the various plants may have been changed as well. In particular, amount of lignin may have increased in proportion to lipid, carbohydrate, and protein. And paleontologists have used the number of species of a particular group as a criterion for their abundances. And extrapolating from this information to actual numbers and biomass is very hard. So from the on land, they look at some specific species, and their abundance can be correlated to the maybe coal or the hydrocarbon in the onshore. In the ancient sediment, preservation of the organic matter in sediment is favored by high organic activity, by optimum sediment weight, and by anoxic condition. Major organic concentration is, as we talked, late Jurassic to early Cretaceous sediment. And people do the modeling to reconstruct the movement of the continent through the time and the pattern of the water circulation, and they can track down the organic matter deposition distribution. So if you look at the distribution of the currently discovered oil and gas reserves through the geologic time, late Jurassic here, right? So, and here. So concentration of the source rock in the late Jurassic to the early Cretaceous sediment. So this is very important fact that we found many source rock of the hydrocarbon in this particular area. Okay. Then, so far we've seen that origin of the hydrocarbon. So how this hydrocarbon, where it's from. So, and people think that this is from the organic matter. And then how this organic matter can transform to the hydrocarbon. So what happens to this organic matter when buried in a steadily subsiding sedimentary basin? As time passes, barrier depth increases, temperature and pressure increases too. So this organic matter will go through these three processes and it becomes the hydrocarbon. So diagenesis, ketogenesis, and metagenesis. And diagenesis is the phase occurs in shallow subsurface and near normal temperature and pressure, and includes the biogenic decay aided by bacteria and abiogenic reaction, and it gives off methane, carbon dioxide, and water, and the kerogen. And net result of the diagenesis of the organic matter is the reduction of the oxygen content, leaving the hydrogen-carbon ratio constant. So kerogen is the kind of a metastable or transient stage before turning to the hydrocarbon. And ketogenesis is the where it occurs in the deeper subsurface as barrier continues and temperature and pressure increases. So petroleum is released from the kerogen during ketogenesis. So first oil and later gas. So from the kerogen to the petroleum, this reaction is called the ketogenesis. And when the kerogen is transformed to petroleum, you have a first oil, long hydrocarbon chain, and then later you have a light hydrocarbon chain. And the metagenesis is the breakdown of the long hydrocarbon chain. At high temperature and pressure, working on the metamorphism, last hydrocarbon generally, that if you break down the hydrocarbon, then the last unit that you will have is the methane, right? CH4. So methane will be expelled. Huh? So we have a diagenesis, ketogenesis, and metagenesis. Diagenesis from organic carbon to kerogen, and kerogen to hydrocarbon is the ketogenesis, and hydrocarbon breakdown of the hydrocarbon is the metagenesis. And we look at the diagenesis. So there are many known bacterial activity, like this one. You have a sulfate, then it becomes the sulfur and the oxygen by the sulfate reducing bacteria. So in reducing zone, anaerobic sulfur reducing bacteria desulfur remove the oxygen, and in upper oxygenated zone, this sulfur will be also again oxidized to the sulfate. And iron can be also form the ferrous hydroxide can form the pyrite, and sulfate ion may also react with the organic matter to form the hydrogen sulfate. So there are many various bacterial activity or microbial activity or biogenic activity decomposing the organic matter or and forming the hydrocarbon or the kerogen. And there are three representative and major reaction. Oxidation generates the water, carbon dioxide, nitrate, and phosphate. Reduction of the nitrate and nitrite. And reduction of the sulfate generates the hydrogen sulfide and the ammonia. So these are the simplified process of biological decay of the organic matter. And in reality, organic compounds are diverse and complex, consisting of protein, carbohydrates, and lipids and lignin. And so that it can decay, but protein decays the fast, and the lignin is the most stable, so that it's a slow process. So as you go right side, it's more stable. By the enzymes of the carbohydrates, such as starch and cellulose, broken down to sugar, cellulose is also converted into methane and carbon dioxide. And the methane is the major byproduct of the bacterial decay of the many organic compounds. So in the coal bed, you found the pore space is filled by methane gas. So lignin can be transformed to the coal, and also it generates the methane. So you have both. Always you found the methane together with the coal. Again, this biogenic methane moves upward from the decaying organic matter. It may cross the this redox potential surface and can be oxidized. Then it will become the carbon dioxide in the water. And protein becomes the amino acid and peptide, and the lipid, and the fat becomes the glycerol and fatty acid. And the lignin of the woody tissue becomes the phenylaromatic acid and the phenols. So this is the this process of production of the kerogen. So with increasing barrier depth, the pressure will increase so that it will compact the sediment. So first 300 meter barrier porosity decreases to from 80% to 30%. And during the compaction, the water will escape. Water is being expelled, but this water contains the CO2 and methane and this hydrogen sulfide and the humic acid. And inorganic reaction generates this oxygenic mineral, the pyrite and the siderite. And calcium carbonate cementation occurs by direct precipitation or by the interaction of the calcium sulfate and the organic matter. And sulfate ion react with the organic matter to produce the hydrogen sulfide and this bicarbonate. Essentially, it will produce react with the organic matter and produce the carbonate and the hydrogen sulfide and the carbon dioxide. So with increasing depth, temperature increases, and biogenic reaction gradually declines as they die out. At the same time, increasing temperature allows the inorganic reaction to accelerate. So this will produce the kerogen ultimately. And we talked about the kerogen, and this is the chemistry of the kerogen. Kerogen is the term applied to the disseminated organic matter in sediment, which is insoluble in normal petroleum solvents. So if you find the kerogen in the rock, then you also find the source rock that may have produced the hydrocarbon. And this insolubility distinguishes it from bitumen. So bitumen is very thick asphaltene material, right, with like the oil sand. And this bitumen is can be dissolved in this solvent, petroleum solvent, but this kerogen is not. So kerogen has three types, generally different hydrocarbon. Three types are this one, alga kerogen, and liptinitic, and humic kerogen. And type 1, type 2, type 3, so agar and liptinitic and humic, they have different composition and consist of the carbon, hydrogen, and oxygen, and with minor amounts of the nitrogen and the sulfur. So that by looking at the chemistry of the kerogen, you can identify whether this hydrocarbon organic matter is from like agar or like zooplankton or phytoplankton, etc. So just briefly, let's just glance through it. Type 1, the agar kerogen essentially is from agar, and lipids are the dominant compound in this kerogen. And type 2 is liptinitic, that's intermediate between 1 and 3, rich in aliphatic compound, derived from the zooplankton and phytoplankton. And the last one was humic. Kerogen has a much lower HC ratio and chemically it's rich in aromatic 1. Humic kerogen is produced from the lignin of the higher woody plant on land. If humic material buried as a pit through diagenensis, it becomes coal. So lignin and humic kerogen, and it becomes the coal. And type 3 kerogen tends to generate largely gas and a little oil. So identifying the nature of the organic matter in a source rock is beneficial to assess accurately its potential for generating hydrocarbon and to consider the quality of kerogen and the quantity for the commercial production. And larger than 1500 ppm total organic carbon, TOC, is the minimum requirement for the further exploration of the source rock. So this is the kind of a criteria for the further exploration of the source rock.